Very nice blend of different locations, disciplines, expertise. So when Eric invited me, I've been thinking, you know, what should we? I teach a lot of these courses, okay, and occasionally, you know, my experience shows that it's good to structure these things a little bit. So that's why I put together this one page, web page that is, not one of these, a web page that has essentially it serves as a table of contents for us with appropriate links. Was this circulated? If not, what we can do is just open up your browser and then just type in soccer, S-O-C-R, soccer news. The Statistics Online Computational Resource is the one that I founded back in 2002 at UCLA before I moved to Michigan. So the acronym is SOCR, or soccer. So if you go to the soccer news page, there's lots of activities here, but the page that you are going to be interested in, and let me see if I can zoom in a little bit. Oh, sorry, the navigation on the Mac is a little bit different. So right up here is what you need to click on, and that's what I have opened in this window. So logistics, we're not going to go over the logistics, but Eric had put together this Trellis forum. I know everybody has, you know, said hello on the forum. We know kind of each other, but now we can put some of these names and faces together. So today, on the 10th, I was thinking of presenting statistical computing tools. So what I want you to keep in mind is that some of you are doing DTI, some are doing fMRI, a lot of people are doing EEG. No matter what modality or signal you're looking at, the statistics are always the same, with one exception. And the exception is whether or not your statistics are defined on Euclidean spaces. So, you know, for the engineers here in the audience, you guys probably know what Euclidean spaces are, right? The engineers, Euclidean spaces versus manifolds. Does everybody know the distinction? Manifolds are curvilinear spaces where distances are measured in geodesics. Okay, so you can think about, we've seen this model before. I have one in my office of the cortex, right? You can very easily have, you know, a fold, a sulcus, connecting two different gyri, right? And I'm looking at how far apart are the tips of the gyri, and obviously they can be close in the three-dimensional Euclidean space, but very, very far when it comes to tracking down through the white matter fiber tracks going from one place to another, right? So that's the notion, that's the simplest notion of a difference between Euclidean statistics and manifold-based statistics. So manifold is a mathematical term that's used to describe spaces that are curved. Distances are not straight lines. Distances are not defined as Euclidean distance between 2 points in space. You have to track some of these geodesics, and the cortical surface is a perfect example. So, back to the story that I started in the beginning, it is very important to recognize that when you do statistics, if things are Euclidean, it doesn't really matter if you're looking at a structural, functional, diffusion, electroencephalography, or any kind of other signal. You know, there may be time, there may be space associated with these signals. The statistics are always the same. So we're going to be focusing mostly on the analytical aspects, and we're going to give you examples, you know, with certain modalities. And if any one of you has any specific data sets that they're interested in perhaps interrogating or analyzing using some of these techniques, by all means, we're going to have a chance to do that either while we're here together or perhaps after the workshop is over when you go home. You're going to have a set of tools in a toolbox. That's my point here, is to illustrate to you a bunch of tools, and you're the one that decides when, how, and whether to use these tools, right? This is just, you know, a view at the window, and some of the other presenters are going to do the same thing. They're going to offer you various tools, and you're going to kind of cherry pick the ones that you're interested in. when it comes down to fitting your specific needs. So, in the first section today, we're going to be talking about statistical computing. So I'm going to, and we're, I know, I might be the only instructor here that uses R, but I'll justify that, you know, choice in a second. So, you know, these are some of the things that we're going to be talking about today. I will try to leave plenty of room for us to do hands-on practice on some of these things. But we should get started. And I wish they had a microphone stand so that I can use both of my hands, but I may have to juggle here because I can't type, control a mouse, and hold a microphone. So let's go. So this, every one of those things is a link. You know, you can obviously keep that agenda page intact. Always right-click and open in a new tab. Well, first of all, is everybody here with me? Were you able to find on the soccer news that specific page? It would be very useful for us. We're not always going to be all of us on the same page, I know that. But we need to be roughly on the same chapter, if you know what I mean. Right, you guys? So let's try to, I don't know. I know it's difficult, but if you raise your hand, we'll pause. We'll make sure you catch up with us. So what I want to make sure right now is that everybody did what I did a second ago. When I did the web search here, soccer news, I went to the soccer page, and then one of the first things here is where I clicked on to get this agenda. Okay, so I'm going to keep that page open because I want to route everything from here. So let's start off with this motivation first. I'm going to open the motivation.
Just click a play to display.
Oh, I beg your pardon. Oh, so yeah. Well, that's exactly why I don't like these wireless things. At Michigan, they also want me to connect this, connect that, but it's got 60 minutes or something timeouts. So if you guys do lose the connection, especially in the back, that I can see. And I think this is wired connection. But the one in the back and the little monitor, if you lose that connection, do shout out so that we can reconnect. So let's start off with some examples, okay? So my point in this first day is to convince you of several things. First of all, the data we all know is large, but no matter what type of data you're looking at, one of my points is that it'll have common characteristics, and these are the ones I want to explore and go after, okay? So I'm going to look at a few motivational case studies now, just to show you where I'm coming from, and I want you to think individually about some of your own data sets or case studies that you have seen, some of your colleagues has, your collaborators have, that may resemble some of what you see here. So again, I'm going to try to zoom in a little bit. And let's see if we can try to... Okay, that's going to work. We'll make it a little bit bigger. Again, you don't have to see every little thing that's on this page because you have it in front of you. So again, just to make sure, I know I hate repeating myself here, but I'm going to be navigating kind of this way horizontally, and I didn't click on the data science and predictive analytics. I'm just going to selectively go over some of the important chapters of this book. So if you guys follow with me, that will be much more helpful than just staring at the screen that I'm showing necessarily. Okay, so all right, so a few keywords here. You're going to be actively learning about driving motivational challenges, computational statistics, and scientific inference. And the first thing that I mentioned, we're going to be going over some driving biological challenges or motivational problems. So the first thing I want to start off with is Alzheimer's disease. Everybody knows about Alzheimer's, or at least the physicians know about Alzheimer's. Progressive neurodegenerative disorder that's typically associated with aging. However, there is hereditary version of Alzheimer's where people get Alzheimer's disease dementia symptoms early on, even in their 30s. In general, you know, if you live long enough, you're guaranteed to get Alzheimer's, just like if you live long enough, you're guaranteed to get cancer. It's one of those things. It just happens. But Alzheimer's disease is very interesting because the prevalence of it doubles every 5 years or so after the 7th decade of life. So you can imagine that human populations across the globe are aging, right? There is proportionally fewer younger individuals supporting the elderly. In different countries that means different things, but typically 70s and older. And I know this is a distant future for you guys, but we are all heading there, hopefully. So, you know, questions that arise very often are identify relations between observed clinical phenotypes. So, in Alzheimer's disease, before you become demented, you're in a state called mildly cognitively impaired, or MCI, okay? And, you know, in this state, most people are actually diagnosed during that early phase, but there is a scientific research hypothesis that says that Alzheimer's disease onset, the beginning of the disease, is probably a decade, maybe even 2 decades before the symptoms become clinically manifested. Okay, so the question is, some of these clinical phenotypes, you know, that we observe, how are they associated with behavior and other things? We are interested in prognosticating future cognitive declines, and I think I'm going to show you some of these examples of how can you prognosticate future cognitive decline. And thirdly, derive and interpret classifications of subjects into clusters using harmonized and aggregated data from multiple resources. As far as I'm concerned, in 10 years from now, obviously all the health data is going to be digital, but that's not the problem. The problem is that we're going to be having data arriving from multiple streams where the data is so incongruent that it's just not clear how to put it together into a single computable data object. You can't do any statistics holistically on the entire data set if it's piecemeal, right? Currently, that's the state of the art. We have, for this collection here, the Alzheimer's Disease Neuroimaging Archive. We've done many of these studies. Some of these are referenced here. You know, you can look them up. ADNI stands for Alzheimer's Disease Neuroimaging Initiative. They have genomics information, including whole genome sequences. They have clinical data, okay, assessments from the physicians. They have biological samples, cerebrospinal fluid, blood, urine, you name it, they have it. They have imaging of different types, including, for many cases, positron emission tomography, structural magnetic resonance, functional magnetic resonance, SWI, you know, and various other things. And then you have family history and all kinds of other things. So if you think about it, for every individual, how is the data represented? The current state of the art, believe it or not, is the geneticist gets the genetics data, they analyze it, and they provide some genotypes for you. The neuroimagers, the brain mappers, they take the imaging data and they extract some neuroimaging biometrics. The physician says, forget about the geneticists, forget about the brain mappers, I know what I'm doing, I'm going to just do the cognitive assessment of these individuals, and I know how to predict what the cognitive decline is going to be. And obviously the pathologists, the ones that actually open the brain, post-mortem, slice it, they take samples, you know, they look at these things, they do their own things. And it's very difficult to jointly, holistically analyze the data. So in the next 10 years, we got to crack that problem. The problem of aggregating and harmonizing data that does not come from the same, it doesn't come on the same basis for the engineers and the computer scientists here. You know that to represent objects, you need to have a base representation. This could be functions, this could be algebras, this could be, you know, you need a common representation, and we don't have that yet. So there is, you know, just look at some of these. I'm not going to certainly read all of these things, but there is thousands of subjects in the ADNI database. It's all publicly available. You can go ahead and submit an application. They approve them pretty fast. You can download every one of these modalities, look them up, and we're going to show some examples of the ADNI data later. And some references, you know, look them up. Parkinson's disease is another progressive neurodegenerative disorder. We recently published a paper where we looked at these UPDRS, Uniform Parkinson's Disease Rating Scale. These are clinical assessments of Parkinsonian patients. And Parkinson's is a disease that's typically manifested by rigidity of body motions or various motion abnormality, movement, and so forth. So there is another very large initiative, something called the Parkinson's Progressive Markers Initiative from the Michael J. Fox Foundation, led by Michael J. Fox Foundation and some other foundations as well, that collects data, and there is, again, thousands of different subjects, all kinds of cognitive tests, as you can see, multiple time points of the individuals, and a variety of things come up here. For instance, not everybody has exactly the same regular observations at 6 months. An individual skipped month 12. Somebody died in the middle, lost to follow-up. You know, sometimes when people study Parkinson's, one of the key elements is how do you prevent falls, literally falling on the ground of these individuals. That's because the most common is falling, hurting the head, or breaking an arm. And for elderly individuals, any one of these could be devastating. So what happens if somebody has an inclination of falling, right, and they just completely immobilize them? They put them in a wheelchair, they get controlled, so no more falls. Doesn't mean the individual improved. No, it doesn't. It simply means that the environment that they live in is controlled, and then you're interested in, okay, well, you know, this individual continues to be part of your study, but now, in the beginning they had falls, now they have no falls. So whatever these guys did worked. No, it didn't. Because it's simply a phenotypic change caused by the reduction of the physical exposure as opposed to change in what's happening in the brain. Is everybody here with me? So you got to be aware of some of these intricacies when the data changes longitudinally with time that has nothing to do with improvement or decline or anything like that. Okay. There's another case here with drug abuse. Again, similar questions arise there. Look at the heterogeneity of the data sets that we have. Amyotrophic lateral sclerosis, Lou Gehrig's disease. Who's the most famous ALS patient that most of us know about? Stephen Hawking, exactly, the famous physicist. So we have a very large collection, something called the PROACT archive. There is 8,400 or so, 8,600 individuals, and we've actually looked at, and we have a manuscript right now in peer review. It's a very, very hard thing, okay? The noise level, the biological noise level in this enormous data set that has, let me just see how many. There were close to 1,000 features for every individual. Of course, there is lots of missingness, a lot of NAs, a lot of problems. But the biological variation that we see between individuals is of much higher magnitude than the actual signal that you get. And when you look at ALS patients, they are tracked by something very similar to what we saw earlier for the Parkinson's, except that in this case it's called ALS Functional Rating Scale. The Amyotrophic Lateral Sclerosis Functional Rating Scale is the clinical assessment. It has 48 questions, and then they get ranked 0 to 4. And the question is, can you predict, looking at baseline, at point of diagnosis, baseline, and 3-month follow-up, so you have 0 and 3 time points, and you got all the clinical data for these 2 time points, but then you're looking 9 months into the future and trying to predict the 1 year decrease of the AOS-FRS score as a clinical biomarker. And it turns out that it's difficult. The variability within subject is large, number one. The variability between subjects is large. And the actual decay for these 9 months, from 3 to 12 months, the actual decay is much smaller. Does it remind you of a situation where you look at functional imaging, where the same thing arises? In fMRI, everybody knows that the signal-to-noise ratio is something like 4%. It's crazy. The signal is this much, the noise is this much. You know, how are you going to detect that? Well, in fMRI, people have figured out that the fundamental law, the first fundamental law of probability theory is called the central limit theorem. Okay? It basically tells you that if you were to average signals, what happens? What does averaging do, the engineers? Right, right. Averaging does denoising. Okay? So that's why in fMRI, you've got these epochs that you say, okay, we're going to, you know, acquire, what is it? 128 time points, you know, whatever. We're going to make sure they're aligned, you know, and then we're going to average. Why average? Well, because when you average, the real 4% minuscule change in the functional metabolic activity that pertains to the activation task, it's a minuscule 4%. But when you average, it's not going to wipe it out. But the noise is stochastic and it's typically zero mean. It doesn't have to be Gaussian. But when you average these noise characteristics, then the central limit theorem tells you that the variability of the sampling distribution of the average goes down to zero, right? So, you know, this is very powerful. You know, the mathematics of this has been known since, you know, the 19th century. You know, people had worked that out almost 200 years ago. But recently, you know, and when I say recently, I mean in the past 20 to 30 years, people figure out that this has direct application into functional magnetic resonance. And the basic idea is, again, that instead of looking at the raw signal, you're going to be looking at averages. And the distribution of the averages is known. You know, this is one of the crazy facts, you know, in the universe. Why is normal distribution called normal? Everybody's familiar with the Gaussian normal distribution, right? Right? Well, why is it called normal? What's so normal about it? Well, turns out the Gaussian normal distribution is the center of all distributions. You know, it's the black hole of all distributions. Think about, you know, we have something called the probability distribution project. You can look it up. We have hundreds of distributions. Well, you take a sample from any one of these 100 distributions, you start averaging the observations. Well, they all kind of converge as the sample size increases down to this point of gravitational balance that we call the normal distribution. Okay, so we know many of these things, and that's some of these statistics come into play when you talk about fMRI. Now, okay, so these are some examples. I'm going to come back to them in a second, but before that, let me just show you this brain visualization tool. And now, if we all try to access this at the same time, it's not the server, but the local wireless connection, because we're all connected, might be impacted a little bit. So what I'm going to do is, you can try to follow that as well if you want. I'm just going to try to open, and for this you have to use Chrome. Safari ain't going to do it, I don't think, because they are not using the Google WebGL plugin yet, as far as I'm aware. So, but if you have a Chrome, I can open this in the next tab. And this is a good tool to remember. This is one of these, remember I told you in the beginning, we're going to be providing you with a bag of tools that you're going to be borrowing liberally later on. So what's happening now is, just to show you, so I'm kind of hiding some of these things out here for you, but this is the address, so it links you to the brain tool. Now, maybe I'll show you a little bit later. Drag in and drop in any three-dimensional volume that is in one of these formats. I'm not sure if you guys can read this, but NII, nifty format, compressed nifty, analyze format, ING, the NGH format, nerd format. So these are structural brain volume formats. dragging it from your desktop and dropping it into that canvas is going to render the volume for you. I'll show you in a second. But it also allows you to do fiber tracks in TRK format, as well as models, as well as shape models of, obviously, two-dimensional manifolds. Remember these curvilinear spaces that I told you about? So they can represent, you know, the different lobes as you can have in this brain. They can represent subregions of interest. But a two-dimensional manifold in the brain, in the brain mapping community represents what's called a genus zero object, which is isomorphic to a sphere, or to a bottle if you want, that's closed cap. It's got an inside and an outside, okay? Doesn't have any holes or handles. That's a genus zero object. And you can drag and drop it in here and it's going to render it. Now, to ease up, you know, if somebody is working on EEG, you may not have any of these data. So we have preloaded various data sets that you can kind of load in by clicking on one of these tabs here. So I'm going to start the first one. So what's happening now at this point is, if all of us do this together, about maybe about 30 to 50 megabytes get transferred from the server that's hosting that app to your local machine. All the rendering happens locally, and that's why you can see, you know, the soccer resort has close to 14 million users in the past decade. Lots of users. We can support lots of users because all the computing and all the apps run locally on the client side. But you still need to send the instruction set back from the server to the client, and that's what this progress bar here, if Eric's computer and the local network can handle that, is going to show in some time. You know what? So I'm going to let this run. At some point it's going to finish loading. Okay, there we go. Okay. So, so this is a truly three-dimensional rendering tool that works directly into your browser, as you can see. And now you can navigate. This is a very simple thing. You can navigate. So which cardinal projection plane am I moving here? This is called the sagittal view, right? From the I'm looking now on which side of the brain am I right now? This is the left side of the brain, right? And I was looking, this is the eyeball here, you guys. Can you see the left eyeball? So that's why I know, and this is obviously the mid-sagittal plane. So that's how you know your orientation, and believe it or not, orientation is one of these crazy things in brain mapping. You know, careers have been built simply trying to find out where is the left and where is the right. It's incredible. You look at this set, it's easy. Here is the eye. It looks like left eye. No, 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 no. Nothing is easy when you start talking about brain images, because it's very easy to twist it. I can take this image, reorient it this way, and you're not going to even know that the two sides are switched. Just mirror imaging. You know what I'm saying? So anyways, so you can navigate this thing here, and obviously, you know, this could be your own image, and you can just rotate in this case. So what I'm going to do is I'm going to go back and show you one slightly more interesting case. Right here is the back button, and I'm going to show you now one with models. This one has cortical surface parcellation models that we've built. Again, these could be for a single individual or for a cohort. See, in brain mapping, the most important question that people ask is, where is something happening? And the answer to this question of where is something happening is very difficult, right? Does everybody understand why? Because human brains are not like a globe, right? The globe, I can look at the globe and I can give you longitude and latitude, and you know exactly where you're sitting. And if you give me altitude as well, I know perfectly where you're located, right? With the brain, it's not this way. Some people have these gyrus, some people don't. So, you know, localizing activation, localizing atrophy, localizing physiological response to something, it's very difficult. So, people have built these atlases. Some are called deterministic atlases, and some are called probabilistic atlases. obviously the probabilistic atlases, I can show you some movies. These regions, they look like clouds, right? The farther away from the center of the cloud you go, the lower the probability that that specific location is part of the region. And as you go towards the middle of the cloud, the higher the chance that this specific location is part of the region of interest, right? Is everybody here with me? So, in this specific case, you're looking at something which is, and you can kind of pair through right in here, so I can kind of go right inside of the brain and do the same thing, right? I can kind of navigate, and if you're really good with three-dimensional games, you can play the game of which region is the purple region, you know, stuff like that. And the last example that I want to show you here, specifically for the diffusion folks, or people that are interested in cryptography and various other things, is this example, which loads in the raw MRI for an individual. It loads in the parcellated brain for the same individual, and loads in the cryptography lines for the same individual. Now, I'm not showing you how to compute the models, the cortical surface models, or the cryptography. We're going to talk about it later. But now this is kind of showing you how you can render these things and view them in real time so that you can communicate. This is mostly used for you know, sitting around with colleagues and talking about what you see versus what was. This is a little bit qualitative, right? And from what I gather, most of you are quantitative scientists rather than qualitative scientists. But let's not discount completely the qualitative aspect of things. Okay, it says it's loading, almost done. Now this one is a little bit heavier because again, it transfers not only the images to us, but the labels for the atlas, as well as the track lines. Okay. Just give it a second here. Is anybody able to get it to work? Maybe I'll come back to it a little bit later then. It will load at some point. So it kind of looks like this is just a snapshot that I have included here. And you know, here is the white matter tracks. Again, they're kind of color coded based upon the direction of the corresponding tracks. You know, tracks that are preferentially red are going side to side through the corpus callosum, connecting the right and the left hemisphere. And these are the important tracks. I don't know if you've heard about, there's various disorders, mostly epileptic related disorders, where people have to actually go in and separate the two hemispheres. Why? They have to surgically split the two hemispheres. Why do they need to do that? That's very invasive. It doesn't get any more invasive than that, other than back in the 19th century when somebody shows up symptoms of insanity, they would literally go with a hook through the nose and pull out half the hemisphere. It was crazy. These French guys, the neuroscientists back in they're called phrenologists, you know. They'll kind of put their hands on your skull, and based upon the bumps on your skull, they'll tell you how smart you are or how crazy you are. It was crazy, you know, back in the day, 150 years ago, you know. So back then, that's how they would do science, you know. And if you don't respond to quote-unquote treatment, which in the 19th century was, well, saline solution and constraints basically, they literally go in and take half your hemisphere. So the next thing that we're doing still is we're actually literally separating two hemispheres. Why do we do that? Normal people, yeah. Yeah, so to stop the progression of epilepsy, right? Because it starts somewhere and it progressively spreads all over the place, and you're trying to, you know, people typically know where it starts, especially in the extreme cases. They have monitors, headaches, they put them in EEGs and whatnot, and they kind of see the propagation, the wave of propagation of you know, some of these things. And if it crosses the two hemispheres, when it gets very debilitating, they have to try. But when you truncate the two hemispheres, you can't do synchronous clapping of your fingers, because the synchronization requires a signal of certain frequency to travel back and forth between these red fiber tracks that I'm showing you. So it is very important to get these things right. Okay, there we go. So maybe what I can show you here is a few of the little, now here is the corresponding part. You can kind of see, I don't know, it's kind of blurred here, but the cerebellum is red. There is a little bit of a yellow and green and blue. You know, these are different cortical parcellations that I'll show you how to obtain computationally later, okay? But they're superimposed now here on the raw image. And now what I can do, go back to my controls. Go back to my controls. And pair through the skull and the scalp. Sorry, this is a bit sensitive here. Okay, something like this is what I want. And then, and now you obviously can rotate this as well. I'm in the mid-sagittal plane. You can see the corpus callosum, the white stuff right up here. Okay? And now what I'm going to do is I'm going to threshold some of the fibers and remove and kind of hide away, not remove, but hide away the short fiber tracks so that I can expose the most important corticospinal tract, for example, that comes from the spine here, which these are typically green that go up and down. Okay, and then the blue ones are, they kind of go anterior to posterior. They kind of go, you know, back to front, are mostly color coded in blue. The red and the green kind of going inferior to superior. And obviously tracks, right? What are tracks? You know, they kind of wiggle in space. They're not straight highways. You know, they kind of wiggle in space. The predominant direction of motion actually is what you can render. And again, this could be your own subject if you have the MR, which you typically would have, and if you run some tractography algorithm that generates the tracks for you, you can drag and drop them. And if you have the labels as well, you can do these things as well. And you know, you can generate some of these images like that kind of show you exactly something of interest that you want to convey either to the patient, to the colleague, or something else. So for instance, if you've analyzed a whole bunch of these individuals using the same protocol, and half of them have a certain phenotype, disease, let's call it for simplicity, and half of them don't have the phenotype, they're controls or asymptomatic normals, then you can look at how different they are, or you can superimpose on these tracks, and we've done that in the past. You can superimpose on the tracks statistical significance maps, okay? Because the tracks may be different in the posterior part, but not as different on the anterior part. You know, the back to front could be different. All right, so once you're done with this, I would recommend you kill that tab, because it's a hog. It takes close to 100, well, this may take, yeah, 100 to 200 megabytes of RAM. So as soon as you're done with this, close the tab so that you can release some system to the, some resources to the system. Okay, so let's go back to our discussion here of the motivation. So here's an example, one of the examples that we did with 800 ADNI subjects. Pretty well separated into patients, ADs, MCIs, mildly cognitively impaired, and asymptomatic controls. And we use a tool, we developed a machine learning tool about 7 or 8 years ago called the brain parser that splits the brain automatically in some of these regions that are shown here. And they all have a different index and a different label for the region. So, and here's the corresponding name. So left superior frontal gyrus has an intensity label of 21, and it's the first index. On the right side, right middle frontal gyrus has a label of 24, and it's the second, etc., all the way down to the 56th region, which is the left singular, the left insular cortex, that is. So you can read more about it, about the brain parser there. This is another thing that you may want to look at. It's genetic forensics. If you want a little bit of, you know, I always wondered, I must admit, you know, how do they do genetics tests in these crime labs, right? There's a crime committed at the crime scene, investigators collect a sample, get sequenced, usual suspects, they take a saliva or blood or something, and they say, well, the likelihood that Joe Schmo is the perpetrator is, you know, something like, the likelihood that Joe Schmo is selected by chance to be the matching individual is something insane, 10 to the minus 12 or something insane like this. And they do it with only, you know, with a few of these short tandem repeats. You know, they literally look at indicators of these short tandem repeats, and they need very, very small fragment. They don't sequence the entire thing. You know, so if you want to look at this, it's very clever how geneticists have worked out some of these things. And a lot of probability theory, by the way, is factored in here when you do some of these things. So in that specific case, the Howard Hughes Medical Institute is a very powerful funding organization in the US. And how many of you have seen the movie The Aviator? Have you guys seen The Aviator? It was an award-winning movie maybe 10 years ago about Howard Hughes. You should watch it. It's a great movie, great story, a crazy guy, you know. The stuff that he left behind is just mind-boggling. This HHMI Institute is just incredible, and it came to be completely by chance. He didn't want to leave his fortune. The feds, the federal government, were after him, you know, off the record, cameras now. So they were after him to get his fortune. He says, I'm not giving you a penny. I'm going to donate all of my thing to a charity that's, you know. So he donated. Now we have this HHMI Institute doing incredible research, one of the most powerful organizations in the world, you know, completely by chance coming about. Anyway, so have a look at The Aviator if you haven't seen that. Now, the next thing here shows you next generation sequence analysis. This may or may not be relevant. Look it up. We have developed some of these workflows that I'm going to be showing you a lot of during my 3 days here. But these ones do kind of more or less classical genetics interrogation, starting with pre-processing, sequence alignment, basic and advanced quality control, and then you have a variety of things that you feed in as subsequent analytics, de novo assembly, calling number variation, and variant calling and annotation. So we've developed these modules, and I'll show you how it works in practice. These pipeline workflows is what I'm showing you snippets of. We're going to be constructing some of these by hand, you know, and hopefully sharing. I don't know exactly, Trellis is not the right environment to share a workflow, but maybe we can set up, if there is interest, a GitHub for the summer school where, you know, we can push smaller data sets, you know, not big data sets, but smaller data sets, and mostly, you know, protocols, recipes, software tools or links to software tools, and pipeline workflows. Okay, there is something on neuroimaging genetics, and now, so I'm coming back to this subsection 7 here, where I want to look at, you know, all of these things, all of these case studies, and everything that you guys have heard about, and I want to argue that they have 6 common characteristics. The data that comes with these examples And many of the examples that you've seen have 6 common characteristics. And it's very important to understand these common characteristics for 2 reasons. First of all, I use these as a constructive definition of what I call big health data. Very, very crystal clear. Constructive definition of what big healthcare data is. And second of all, these 6 characteristics tell you exactly what kind of tools you need, and it doesn't really matter what disease you study, what data type you have, whatever. You need tools that satisfy these needs. So I've summarized this right up here, 6 dimensions of big data. The first one is obviously size, so you need tools that are scalable. They need to be able to deal with large amounts of data, and large amounts, what is big? What is big when you talk about data? Is 10 megs big? 10 megabytes? Is 10 gigabytes? Is 10 petabytes? Terabytes? What are we talking about? What is big, really? From your own personal, you guys have dealt with data, right? Everybody has dealt with some data. So I'm asking you, what is big? What is big data? Because I'm talking about this thing here, first here, size. What does it mean to be of large size? Terabytes. Okay, he says terabytes. We got some of those now. These are difficult, yeah?
I was just going to say that.
Terabytes as well, okay. Wait a minute, nobody has big data sets that's like 10 megabytes. I can, okay. So during the break or something, come by, I'll show you a 10 megabyte data set. Your eyes are going to get, it's difficult. It's got lots of issues because it's not structured imaging data set. It's got an unstructured. 10 megabytes is a lot of bytes. Let's be honest, 10 megabytes, and I agree, it's not on the order of 10 terabytes, but understanding the 10 megabytes, because that's what you're ultimately going after. You want to know what's the information content in these 10 terabytes, or 10 megs or 10 terabytes. This is very important. So, the point I'm trying to get across is that size is a relative term. It depends upon the data type that dictates when does the data become large. The second thing is the complexity. Everything that has to do with file formats. How many of us have written data format converters? Has anybody written a converter to go from one data type to another, to go from analyze to Nifty, from Nifty to Mink, from Mink to nerds? It's mind-boggling. And why do you have to do data conversion? Well, because you have one tool that wants the data to be in that format, and unfortunately the next tool you want to use wants the data in a different format. So what do you got to do? Well, think about the simplest example, you guys. Intensities of these neuroimages. What is the spectrum of the intensities? The intensity, right, everybody knows when I say intensity, what I mean. I'm talking about the value that's located at a specific voxel element, volume element, right? Specific location in space. I have a certain color that the image includes, and this color could be a vector or a univariate measure, 57 or minus 1.35. Well, okay, so how is this thing stored? Well, it can be stored as a 1 byte value, which has 8 bits. It can be stored as a 16-bit short integer, right? But now that has a twist, because does the integer has positive and negative values in it, right? Or it can be stored as a 3, sometimes people store stuff in 3 bytes. 1, 2, 3, 24 bits. How do you interpret that? And then there is people that store things in 4 bytes. 4 bytes can be an integer, or it can be a float. Or sometimes you can go to 8 bytes if you want to have double precision. So the very, very same image, you look at them, they look identical, can be stored where the colors or the intensities at every location is stored in a different format. So you got to do these conversions. So this is the most common type. So there's lots of complexity that have to do with data wrangling. The wranglers, these guys with the lasso that, you get the lasso and you catch the animal. These are the wranglers. Now they do this with data. Anyway, so that's complexity. Incongruency. Well, incongruency simply means that the data is not homologous. Okay? it's incongruent. Well, think about two brain scans. 1, 2 brain scans. You take these 2 brain scans, are they homologous? No, they're not. They're not in the same space. One was scanned like this, the other one was scanned like that. They're different size, orientation. If you're looking at functional activation, you scan the same individual early in the morning, late in the afternoon, completely different profiles. You know, they're not congruent. So the congruency has to do with the homology. Think about in the sequence world, in the genetics, when 2 sequences are homologous, they're aligned. So you know that every location on the sequence, they're kind of paired, right? And you have for each of these, they're called single nucleotide polymorphisms, you have a specific reference ID. They're called RS number. Okay? So these are homologous, but sequences are, in their native state, are never homologous. You gotta make them homologous. In the brain mapping community, we refer to that, what's the action verb? Homologalizing process as spatial alignment or registration, right? Okay, guys? Okay, so incongruency. The data comes from multiple sources. I already talked about this, right? One comes from the clinic, one comes from radiology, one comes from pathology, one comes from the ER, the emergency department, you know, whatever. And it all needs to be, remember, if you don't analyze the data jointly in its entirety, you are looking at a process through one prism that only shows you one specific type. I mean, early on, the physicists, when they were looking at the stars, what do they have? They have a lens. Makes things big and small, right? That's what they had, you know, think Galileo, you know. And then people realized that if you start putting filters on these lenses, you can actually find the red shift of these stars, which is incredible. Totally incredible, mind-boggling, you know, to look at the red shift of stars. Why? Well, it tells you how far is it, how hot is it, what elements it's got on the star. You know, it was, and that's where broadband. Does everybody know the term broadband when you talk about internet connections? Well, it's the same thing. It's a spectral decomposition of the entire frequency band, okay? And that's why they go, you know, these Gs, where do those Gs stop? We started with, you know, it was in the megahertz spectrum. Now we're 1G, 2G, 4, you know, how many Gs are we gonna? So the higher the frequency, the more signal you can send through those broadband channels. The same thing. So the point I'm trying to get across is that if you're not jointly modeling all the data, and currently we're not, you're looking only through one prism, and you're looking at only one. There is some things that are undetectable from your point of view. Okay, so it is important to understand we do need these tools. Multiple scales. Now that's a beautiful thing. If you think about it, multiple scales. What does multiple scales refer to? Okay, think about scanning somebody, an elderly individual. You scan them before they die, standard high-resolution MRI, functional, positron emission tomography, you know, whatever, the whole spectrum. And then post-mortem, you actually cryotomographically section the brain, and now you pair really deep. You go through the standard microscopy, you go through the electron microscopy, and you have the same object, the same brain, but you're looking at different resolutions from the macroscopic to the microscopic to the nanoscale. You can look at these things with different tools, and that's the multi-scale aspect. It's incredible. It is incredible to look at, and the data, you know, believe it or not, the biggest neuroimage data is not what all of us are dealing with. The biggest neuroimaging data is cryotomographic data, because a single slice at 20 microns is probably a couple of terabytes. It's incredible. But now you're looking on the cellular level, and there is obviously contrast, you know, lots of complex. And now you have to, you know, I don't know how much people are interested in cryotomographic images because they're obviously very invasive, but they kind of give you the true state-of-the-art physical representation of the structures. But now imagine having two slices, same individual, two near slices, maybe let's say half, I don't know, a millimeter apart. These are going to be similar slices, right? Well, not quite. And registration of these things is incredibly difficult, believe it or not. So there's lots of complexities with the multi-scale. And now the last, but certainly not least, is that the data is incomplete. So you have to have strategies and protocols and tools to impute data, because if you don't, you can't do any statistics on things that are like this. You can't do statistics. Things need to be in place. There must be homologies. If you have incomplete data, you know, why is it incomplete? Is it missing due to random causes, or is it missing because of some kind of an underpinning that's either biological or physics driven or something else? So ignoring missingness leads to biased inference at the end, right? You're very likely to have a conclusion or inference that may be biased, right? You're either under or overestimating whatever effects you're going after. All right, so so that's the motivation. The next two things, I hope everybody just read through. It talks about what is data science and what is predictive analytics. Scan over these things. Here's an example of a workflow, and this ends up with a few places where you can find lots of interesting data. I'm going to be showing you some of my data that's available right up here under software case studies. Okay, so some references. So, taking a step back now a little bit, where we came from. So this is the motivation. Any questions or comments before I now move a little bit? So this is just supposed to justify what's coming up. Okay, a little bit of flavor. I know everybody has their own perception. Does anybody have anything to add to that list of things, or any questions that might come to mind before we press on here and go to the foundations of R? So R is going to be this computational environment that we're going to be using now for the hands-on operations. Any questions, comments, suggestions? Yeah.
I didn't get that part when you mentioned the geneticists. They were studying the crime scene. The short
Tandem repeats. Yeah.
Yeah. So what's the point?
So the point is that you've got a very small segment. You should do the activity. I did this activity with my kids. They love it. So they give you a in this specific case that the HHMI Institute worked out is they wanted to remember 4 years ago in 2013 there was a huge Ebola outbreak in Africa. Okay. And they wanted to know, where did the virus originate? They wanted the kernel, right? Because people move about, you pass it to some, So it was kind of common. So they were interested in how the epidemiologists were interested in. How do I find out where the virus originated? So what they did is they went for patients that were infected. They did a cheek swab and they sequenced partially the genome of the virus for these individuals. And then they wanted to compute distances between the viral genome of different individuals. Because imagine, suppose we were all infected here, and suppose two of us have the Ebola virus genome that is close, and two of us have the Ebola virus that's very distant. What does this tell you? This tells you that the virus migrated longer from that point to get to us, and between us it was a short elapsed time, right? So this kind of tells you that we're farther apart. So to determine the distances between the genetic sequences, they use these short tandem repeats, which only includes, I don't know, 100 base pairs or something insane like this. 100 base pairs. The human genome is 23, billion base pairs. It's huge. They're looking at 100 base pairs. How do they do that? How do they do it? Well, they look at how many times do does the viral genome, not the human genome, the viral genome have, how many times do they have these short repeats where the same segment gets repeated in, obviously on the same chromosome, gets repeated, and how many repeats does it have? Has to do with viral mutation is very rapid. In fact, people think that the viral mutation is the best proof of evolution, right? Because you can literally see the evolution in front of your eyes. On the vertebrate level, evolution is very difficult to determine. In fact, it's a real miracle how Darwin figured out that, you know, evolution occurred just looking at these fringes, you know. But on the viral level, it's very, very rapid, and you can almost see it literally from one to the next, you know, as the virus reproduces, it constantly mutates. Well, these short tandem repeats tend to either accumulate or shrink as the virus reproduces. So you literally, it can be done, the test can be done, you know, because you don't sequence the whole genome, you just sequence a small fragment, and you literally count how many times is the letter A in that sequence repeating, and typically it's, you know, 6 to 7 versus 2 to 3, and that's how you measure distances between genetic sequences. So you should look it up if you're interested. It's an amazing, I know, again, kids love to do the game because they get to count, and then they see the C's and G's, and you know, it's an incredible example of a clever way of handling a very complex operation, of finding out the mutation pathway. And obviously, you know, going back in time tells you where the virus originated. Anyways, any other comments or questions before we move to the next segment?